right. Okay, so here we go. What is a theorem? So in mathematics, they give you a theorem, and then they tell you, that prove it. Okay, and a theorem is a statement of a a statement of some mathematical truth. Okay, so what is a theorem? Theorem is a statement. Should I write that down? Yeah, looks well. Okay, so what is a theorem? It's a statement of some kind of mathematical truth. Okay. Just like in our poem, a silken tent was a statement about the truth of this woman, she's sureness of soul, and how her ties and everything, how she exists and interacts with people. So theorem is a statement of some kind of mathematical truth. And for us in this class, most of the theorems we're going to run in are going to be implications, right? So I'm going to say TH as in theorem, THM as in theorem, implication, and attendance, yes. Oh, James, thank God you're here, because I was worried you're going to miss out on pizza. Go get a pizza. Oh, yeah, I can't either. So I'll have to do the Yeah, I'm going to bring dumplings then. Yeah, chicken dumplings is the best. Made by me. I'm not going to take attendance. It's a pizza day. Okay, so you can miss today. All right, so in our class, in the real analysis class, all the statements of some kind of mathematical truth show up as implications. What's an implication? It's this structure. This is the hypothesis. And therefore, this is the conclusion. Is it? Another word for that is antecedent, mathematical sciences, or consequent. All right. Yeah. And then our example from last time was that if n squared is odd, and I wrote this without the is, today I'm doing the is, just for the hell of it. And then this was n is odd. Pizza? We haven't even got to the second one. I know. I have one of my favorite students. He's like 6'5" or something, and he can eat the whole damn thing. Because he shows up on a Saturday or Sunday to do math with me. Yeah? Okay, I'll start doing the Saturday sessions, and then there'll be dumplings and other kinds of treats. Yeah, this favorite student. Okay, I'll try. All right, so here we are. A theorem is a statement of some kind of mathematical truth. And then those who want to go grab a second one are now, please. So you make a line here now, folks. We'll wait for, this is so fucking exciting. It is the best thing that's happened to me. Yeah. If only Americans were generous like me, the world would be such a great place. We're like, we don't have money for Bangladesh. That's American, IMF and World Bank. only if it's high interest rates. I like this. I should take a picture. So beautiful. I'll post this picture. My hungry Americans who are not being fed. You are being paid for this, yes. Yes. Oh, she's going for a smaller piece. That brings shame to the house. I sent an email last night. You didn't read?
I did, but
Oh. Hi, hi. Okay, how am I going to fatten you people? I'm working on it. Okay, cool. Okay, now the next step is, oh, dumpling days. Dumplings are good. I also had pork dumplings that were really good too. I just threw out that bag. I shouldn't have thrown it. I know, I fucked up. Yes, I know. Uh, you should get in the line. I'll take a picture of you. Yeah, here we go. Cool. There you go. All right. Cool, cool, cool. Wow. So there can, after this, there can be thirds if you just get up and go get your third slice, okay? Looks like people haven't eaten for a few weeks. New student, brand new, pizza slice if you're hungry. Yeah. Guess it's gonna be oh, fuck, okay, we're fucking up on time.
matters pizza.
Yeah, it's pizza day.
Oh, okay, yeah.
Okay.
I've stopped worrying about because when we don't have to get to integration, so I'm kind of relaxed about that. Yeah, and enjoy mathematics for a change. Okay, so um, God invented mathematics and gave it to us. Mathematics is the fire that who got the fire? Somebody gave it to the, who was that idiot God? Prometheus. I didn't like what Melania was wearing at the inauguration, that hat thing.
No.
Yeah. Oh, you want hamburgers? Oh, is that what it is? Oh. She went back to the 1920s and 30s with giant jackets and yes. Conclusion and consequent. Okay. All right, so I'm going to restart. And these two friends, just focus on eating. Okay, so there are now one giant weird slice. So, oh no, it's two. Oh, they didn't do a good job cutting. It's American tech. Okay, let's do some math. All right, so we have a theorem in mathematics. Your professor will give you a theorem, and he will say a theorem is a statement of some kind of mathematical truth. He gives you the theorem and says, we don't know if this theorem is true or false. Please prove it. Write the proof down so then I can give this theorem to my children and tell them that you can use this theorem in your life, in your mathematical life. So in our class, in the real analysis class, most of the times we're going to, our theorems will look like implications. So if the hypotheses or antecedent, then the conclusion and consequent. All right, so in other words, when somebody says you need to prove this, that means you have to show two things, that the hypothesis implies the consequent, because that's what if and then is. It's an implication. You have to prove the implication. So you have to prove that there is some kind of relationship between the hypotheses and conclusion, and it goes towards the right. If this is true, and if you can get to this one, then this will also be true. And that means that the original thesis was incorrect and throw it out because the proof showed us that it doesn't work. Now, let's keep doing this. So here you are, and you are given. Another way to generalize this is if we call this one P and this one Q. So the first, this is a statement, right? This is a statement. Let's do the statement business first. Okay. We have a mathematical statement right here. And then we have this statement here. And when we prove this implication, what we have done is we've done two things, that these two statements are related in the relationship of implication. If this is true, and we were able to show that we could deduce from this, derive from this, this second statement. So their relationship is also true. And okay, now this is the hard bit. I'm trying to, what does your professor mean to show this, to prove that this statement of some mathematical truth is correct? What he wants is, he wants the true values. He wants both of these to be true. So if you can show that this implication has a true antecedent or a true hypothesis, and that leads us to a true conclusion or a true consequent, then you have proven the theorem. You need to have two T's. This could be false, right? And then this could be false. And there is that whole tree that goes down, which I'm not going to get into, but you can Google. Now, let's go back again, rewind. So I show up and I give you P, then Q. So my question to you guys is, what is so your professor shows up, he says, prove if P, then Q. Or your professor says, prove if n squared is odd, then n better be also odd. At this stage, what is your first step? Is this true? We don't know. Is this true? We don't know. Is this false? We don't know. We don't know anything about their truthfulness and falseness at this stage. So the first step is to do what? Assume, right? And if you have this arrangement, we assume this to be true. And we don't know anything about this at this stage. So proof, first step. Step one, you're given an implication. Your professor says, prove this implication where both P and Q will be true. You will be able to show that both P and Q are true and they are in this relationship of implication. So step one is you have to assume something. We always assume the antecedent, the hypothesis, the P. We always assume P. Yep, this will help you with your scores on LSAT. Oh, you did? Oh, excellent. Mm-hmm. Because all reasoning is identical. All thinking is identical. Kind of, yeah, unfortunately. Symbolic logic. Okay, you assume P, and then when you assume P, can you start? So all you've done is assumed that P is true. And now you want to begin your proof. So second step, begin writing your proof. So can I start with this guy, Q? And reason, we don't know if it's true or false. where we can only assume this to be true because we're going towards the right direction. If we assume this to be true and are able to deduce, you can, yeah. So we'll do that in a second. So if you assume this to be true, then if you can deduce, derive, expand on P and get to Q, that will imply that some true statement got you Q. Therefore, Q is also true. And then you're going to get two T's here, two truths, and you're done. Okay? So, question again. Our proof, where should it begin? With n squared is odd or n is odd? And answer is P. We can't start with Q because we don't know if it's true or false at this stage. That's the key thing. Okay? Now, and then what does it mean to deduce from P? We bring in all our previous definitions, previous theorems, every fact in the world to help us expand P, expand, make changes to this so that this thing looks like that by the time we are done with the proof. Just like in the poem, the poet expands the idea, the poem Robert Frost's A Silken Tent. He expands on a silken tent where finally he gets to the stage where he can say that now he's talking about the she, the beloved. Okay? All right. So is everybody good right now? Now, sometimes what happens sometimes, folks, it's harder to go from the antecedent, the hypotheses, deduce, derive, expand on the P to get to the Q, because this is probably more useful place. Maybe if n is odd was here, and this statement was over there, you would like, shit, if only this, okay, let's actually write this. Okay, so what am I talking about? So, okay, so if this is the situation, what's our rule? Step one, assume. Assume what? P. If you assume this, there's no way it'll be much harder to go from this to that. I don't know if you can get there or not, but you look at this and you go, this is more fruitful. It has a square in it. I can barely do anything here, but there's a square, I can mess around with that and hopefully reduce it to make it look like that. So in other words, in your head, you're going, oh, if only this wasn't Q, if only the conclusion was over here. So in this situation, there is an equivalent statement. So these two things are going to be equivalent. And I'm paranoid about, I'm recording voice, okay. Just pray for the recording. Let's see. What is an equivalent statement that helps us get Q to this side? And we're going to call this the original. And the term was from last time, contra, positive. Yes. So I want Q here. And I want P here. Right? Because Q is more fruitful. And I can go from, and then I'm going to do a direct proof again. At this stage, I can now assume Q and then derive, deduce, expand, Q, bring in all my knowledge in to get to P. Because I've assumed Q to be true, and I got to P, P is also true, and I'm done. Now the problem is, are these two things equivalent? And the answer is no. How do you make them equivalent? You put a not. Okay, that's what we did last time, and then we looked at why this was okay. I actually explained it better than in the textbooks because all they tell you is if you make a truth table for this and the truth table for this, they're identical. If you start out with the same values of truth or false for P and Q, these two statements will be identical. I think I messed up one little thing. Is if P then Q a statement? Yes, an implication is a statement. Is P a statement? Yes. Is Q a statement? Yes. The implication is made up of smaller statements. So the building block of implications and relations are statements themselves. All right, at this stage, what do? Step one for proof. Assume this to be true. Okay? And how is this going to be true? If Q is false and you negate false, you get the value 2. So that's what we're saying, that the Q itself is true, is false, or only this version is. Anyways, so we assume again the antecedent. And so what do? We assume, in this case, this is the negation sign, or let's just do that, not, and not, because this is not a class on logic. In math, you actually write out stuff, and you try to avoid notation and all that, which is kind of, that's why it's again, is that why we hate math? This is getting recorded. Mm. Mm. Well, I can't say anything to Reese. She fed you. We have one little skinny one left. You're not real, guys. When I was your age, I could eat for a whole day and then go for a run. No, we don't run in Pakistan. That's for idiots. We have servants, they carry us around. Shit, I'll have to take that out. Okay, all right. Is this identical to this? Yes. And so you can use this, and when you prove this is true, you've also proven that this is true, and you're done. Your math professor gave you this implication to prove. You prove this, and your professor said, what the hell, I wanted you to prove this, and you prove this, get out of my office. And you go, shut the These are equivalent statements. This is identical to this. Since I proved the twin brother, it applies to the original twin. Okay, now, this happens a lot, okay? And then what's the third thing? So your professor gives you this implication, says prove it. You try this method, it fails. And you go, oh, I know. So what you'll find out is most proofs in mathematics are proofs by contradiction. So unfortunately, so we're going to formulate a third implication, and so that we can use this method, proof by contradiction. So this is the method. It's not the name of this thing here. So this is the method. This is the original. This is the contrapositive of the original. And then what I'm going to write here has no direct relationship with any of these. In fact, it's its own new theorem that is not related to this or this one. Okay? So does anybody remember? So I'm back here. My professor does not give me the contrapositive. My professor gives me the original theorem. And I'm going to original implication, and I'm going to modify that. So I'm going to go if P, then I have a Q here. And guys, remember from last time? What do I do with Q? Yes, very good. Okay, so at this stage, this is what I'm going to, so what I'm saying now is that I cannot, and okay, before I continue, let me do this, make sure, yeah, it's readable. All right, so let's look at this and this here. What can we say about, I have rewritten, I rewrote the original implication to look like that. So over here, this would be if, let's say if we still have this one here, if n is odd, then n squared is even. I just did a negative on that. If n is odd, I don't touch that. P remains the same. I just negate the consequent. So not q would be n squared is even, or n squared is not odd. You can also say it like that. Now, folks, you have this. What is this telling you? What kind of implication? You know this implication. There's something you know about this implication. And it better be that thing that you know about it, it better be true. Otherwise, this won't be true. This needs to be, exactly, this better be. So we're going to do better. Oh, I'm going to write here, better be false. So this box, this whole box here, that the compound implication, this whole box better be false. If we start doing this proof and we run into contradictions, we realize that our reformulation of the original proof was a bad idea. And it led us to a contradiction, which means that the original theorem, the way it was expressed, was the correct way to express it. That P implies Q and all of that business. Okay? So this is our hope. We are hoping for this. Let's say no contradiction arises and we are able to show that if P is true, we get not Q. What does that say? If we don't run into a contradiction with this, what that means is the original theorem, throw it out, use this. This is the true statement of some mathematical fact. Yes? Okay, now, next question is, so let's go back. If your professor gives you if P then Q, where do you start? What do you assume to be true? And you start here, right? You find that it's too difficult to start with P and get to Q, therefore, you do the contrapositive. Where do you start? Here again. And why is that? Because we don't know the truth value of P, of Q or not P. We don't know the truth value of P. We do not know the truth value of Q, not Q, or the truth value of not P. So we assume, right? That's why it's called in hypotheses. Our hypothesis is that the antecedent, let's let the antecedent be true and see what happens. Let the antecedent. So this letting of things to those assumptions, that's the first step. Your assumptions can be 2-3 lines long in a proof. Okay, now, proof by contradiction. What do we do now? What do we know right now? Very good. What about P? Do we assume P is true? Yeah. We always do that. This whole row is the row that we assume to be true. And then we just did not Q. How were we able to do that? We were saying, if you put a not in front of Q, then I'm pretty sure this is a true statement. Okay? So both P and not Q are true. Where do we start? Because here we only knew the antecedent was true because that is what we assumed. So we could start here and then get there because we didn't know what the value would be. Here, we start here, assume that to be true. And so in fact, in this case, we should start where? This is our real assumption. So we start here. So I'm going to say start here. Because what we're saying is that the negation of Q is related to P in this implication. That is, if we assume P to be true, and we can then deduce the negation of Q from our assumption of P. And we are very confident about that, so we can start here. Okay? All right, now, there is no dessert. Okay, so I know I messed up, and there were no drinks. And let's start doing the first proof, and we might be just able to do a few steps. So I'm going to write that out. In fact, I'll just leave this there. So any confusions or questions? No, you're good? Is Costco pizza, I think they've made them smaller now. They don't look that, right? I think Biden administration told Costco to, otherwise they're going to cancel Costco, so they have to make it smaller because Biden administration is worried about our children's health so much, while he's killing my children over there. Okay, don't make me emotional, Biden. Now, if you buy a microwave oven, which I'm doing right now, I just ordered a microwave oven, there's an extra security button. Everything is national security now, so that your kid can't just grab that thing that's hot. Yeah, while we're bombing people over there, our children must not burn their hands because it's not an implication. If our children are safe, then other people's children will not be safe. Let's prove that. Yes, sir. If you kill other people's children, are you a better person, or if you kill your own children? I have to delete all that shit. And the answer is, if you kill your own children, then you're a better person. Do I really want to kill James' children? No. Then I'll be a monster. So please kill your own children next time, Ben. Okay. Let's do this. So we have n squared is odd. We will assume this to be true, and then we'll try to derive from this statement here, n is odd. Now, in order to do that, we have to bring some mathematical knowledge into the picture. So the first thing we need to say is, so before we even tackle that, let's do some facts. Facts, useful facts, let's call them. So these are true things already in mathematics that we can then apply to this guy. We assume this to be true, and then as we are deducing this, trying to make this get to that successfully, we can also bring in definitions, other theorems. In this proof, which is a very simple proof, all we need to know is this thing. So I'm going to write the statement. Useful fact number one is the unique factorization of a positive number of a positive number, or unique factorization of a positive, I'll just say positive. That's what I have in the notes. So this thing I'm writing is true. When you factorize a positive number, the result is unique. That is, you only get one result. Okay? So if you have the number, let's say 4, how do we factorize this? What are the two factors that go into making 4? 2 times 2, also 4 times 1. Why is the second one a bad choice? Because we want prime numbers there, okay? So we are actually talking about prime factorization. You guys know what prime numbers are? 2, 3, 5, 7, all of that stuff. So when you talk about factorization, you're usually talking about prime factorization. So let's do that. And let's look at another example. We have, what's a cool one? Let's do 20. So 20 is 2 times 10. And 10 is 2 times 5. 2 and 5 are prime factors of 20, okay? So one of the facts we'll be using is that our n, and I haven't actually written the question, which is here. And so once I write that, it will be clear. We're thinking about what kind of a number n is and how to manipulate it. So first thing you know about n is that it's a positive number. And when you factorize it using prime numbers, the factorization will be unique. What does that mean? 20 is not equal to, this is the only, unique means one only. Okay, all right, so that is I think that's the only fact we know. Do you guys know what odd numbers are? 1, 3, 5, 7. Even numbers 2, 4, 6, 8, 10. Even numbers are numbers that can be divided by the number 2. 2 is your friend. Even numbers can be divided by other even numbers. Can an even number be divided by an odd number? No. Can an odd number? Yes, you're going to get 3. This is an odd number, evenly divide, right? You don't get a remainder, you just get. Now I'm going to divide 9 by an even number called 4. Doesn't work out. You don't get a whole number here. I will try another even number 2. Does not work. But if I have an odd number, 9 is an odd number, I can divide it by another odd number, 9, and it works. That was my move right there, or 3. You get 3 there. Okay, is that all very confusing? No? All right. So this useful fact, the fact about how if you're given a positive number, positive means it won't have a minus sign in front of it, it won't be negative, then you can expand that thing into its prime factors successfully. All right, so this is from this book by Haggerty, or whatever this guy's name is. It's a reasonably good book. And the method of proof we're doing is going to be direct proof. We're going to get an implication if something, then something, and we won't have to go to the contrapositive or reformulate the original implication into a proof by contradiction one, where we take the conclusion, the consequent, and negate it, keep the P. So we are just going to do the first, right? Okay, so let me write that. So in your PowerPoint note, it says example 3, and then it continues, assume, and usually you don't get proofs like this, but that's what he's doing here. Assume that, and he's telling us, I'm really nice, I'm a nice professor, I'll let you assume. N, so that your proof can be easy, is, this is N, is a positive number. And he says whole number, I'll just say number, dot. And then the second line says prove that n squared, if odd, no, prove this line here. That's what I have on my PowerPoint. So what's happened here? So where's the theorem? Theorem is always an implication. And here we go. I think we're not going to get to the proof today. Uh, what's another way to write this? P implies Q. These two things are exactly the same. So in math, we are not really supposed to do that. Sometimes you're in a hurry. So that the textbook author was in a hurry and wrote it like that. Okay? All right, so now here's the key trick here. To do this, everything before the then is going to be something we can assume to be true and go with it. So the way this thing is stated, what are the two things we can assume? So we can assume the truth of unique prime factorization, and then what else? What are the two other things that will come into this proof? Hint, hint, everything before the then will be our assumption. So, anybody? Russell? Very good. And anything that comes before, and n is a positive number. So n is going to be a positive number. It's not going to be a real number. It's not going to be a rational number. It's not going to be an integer. It's going to be only positive number, which means positive whole numbers. So no decimal numbers. What's a positive whole number? 1, 2, 3, 4, 5. What's another way to write this, which I did last time? Assume that n is natural number. Okay, all right, so now let's start the proof finally. So where do we start? This is our implication. Pretend there's an if there and a then. So we can start here, or we could even start with this assumption. We could perhaps start here, get here, and then go there. Okay, let's do that. Because this is one of the things that this line here, I'm putting double lines for all the possible places we can start. These double lines indicate this is all the hypotheses or antecedent. So first line, what should I write? I want to expand n, right? So I'm going to say let, this is not, it says when in the PowerPoint. I'm going to do let n equals. So if n is 12, 12 should equal to what? 2 times 6. 6 is 2 times 3, right? But we want to do this this is a concrete example of a positive number and its unique prime factorization. Is this thing identical to this? Yes, you can write this or you can write this. So we take this assumption that n is a natural number or a positive whole number. So I write n, and I'm going to now equate it to its prime factorization, which will be unique, one and only. Can I write 2 times? When is this true? When n is 12, right? So what do we need here? Something that's always true. So let's do P1 times P2 times P3 times forever. And I'm going to rewrite this in the way, so let's make this slightly easier. So did you guys write that? So you want to just write P1 times P2 times P3, however long this unique factorization has to be. Now, How many people are confused about this? What's happened here? Is n equal to this product of many primes? Yes. Okay, so we have done that. Why are we doing that? Apparently, this is a fact that you had to use in a direct proof to get to where we need to get to. Okay, next. What should we do next? We took this assumption, this is part of our hypotheses, and expanded it. So what we basically are doing is, what is the definition of a positive whole number? For this moment, the definition is that it's a product of prime factors, of primes. Now we want to go here. How do we express this like that? So we square this and it will look just like that. Okay? And at this point, also, by the way, this is assumed to be true. And we don't know if this is true or not. Hopefully it will turn out to be true if we can get from here to there. So we square it. So how do you square something? You do you want me to put parentheses around it, or is this good enough? And then if you are squaring a product, I could either do this, and then what happens? Then you take the 2 and apply to each of these. These are all rules that you learn, but if you take a math class, they'll actually have theorems and definitions about that. So I'm going to square P1, I'm going to square P2, and I'm going to square P3, and I'm going to square by putting these these ellipses to show that I've squared every possible prime factor to the right. Okay, now we're looking pretty good. Now we started with our initial assumption, and finally we expressed. So what have we done? We have deduced from n squared is odd, this thing here. And then can we say that this thing is odd? So we can say that because that is our assumption. So I'm going to write this thing is odd. Again, when you go home and you're feeling bored, look at the PowerPoint for that. It's done slightly different. So because that is our assumption, how many numbers are there in this box? 1. It's either this, which is identical to this. Okay, and then we are told whatever this number is, okay. So I'm going to restart here and not go back to the original. Is everybody super clear? And no dumplings on Monday. It's going to be a Friday thing. Yes, because I know as the semester goes, people are going to not show up on Fridays. So, oh, we could do a potluck Friday. Ah, that would be cool. I'll bring my cat. We'll eat other people's food. Oh, no, I don't believe it. That's fine. Okay. Yeah, okay. There are 2 pieces there if anybody wants to take them home and try to kill your roommate with this. All right. So everybody's cool. Russell, you understand it better than last time? It's getting clearer? Yeah, okay. You too? Okay, cool. Thank you, guys. Oh yeah, please. Well, I didn't do attendance today. Yeah, bye. Mm-hmm. Mm-hmm.